Ciao, and welcome to the Frontier Space Podcast, a dialogue about how space technology and exploration are transforming our solar system. We're excited to hear from Dr. Manoj Tripathi, who is a researcher in materials science from the University of Sussex in southern England. Manoj specializes in nanoscale topographical characterization of hybrid materials, semiconductors, 2D materials, carbon-based polymer composites, Straintronics, and other applications.
Okay, so the one of the motivation actually behind is the problem that having in the nanoscience, especially related to the 2D materials. So it the including the Nobel Prize, but I think the research has been a long working in this field. So there is a problem that why one part of the world is getting good property, but another part of the world is not getting the same. Means that things are not reproducible, not scalable, although we have discovered this material a decade ago, thanks to Manchester's group. So this is the motivation behind. So what are the reasons that is causing this the changing of property? So then the role of the defects come into play. I'm not talking about the defects that you implant. The defects naturally happen in this material, because if you look the top research, they say that the graphene is stronger than steel. Then why it is not acting like a steel? So that was the motivation. So we found that actually graphene come with the package of structural disorders, vacancies, grain boundaries, wrinkles, and these things are affecting its mechanical integrity. Then question how much it is affecting it. So that's a part of the paper. But we have found that not only it affecting mechanically, but also affecting electronically. Because if we go down to the sub nano level, we talk about atoms and all this. So we have found that these defects basically, defects is not always about there's a vacancy. If there is some structural disorder, let's say you have a proper square, and at the corner someone beat it up and the square changes, so it's a deformation but not defect. So the structural deformation, like if you consider graphene as a flat, if there is a kind of like a wrinkle that we see in curtains, a kind of like a hump, so that is considered as a structural disorder because it is not flat. Because if you see graphene at atomic scale, looks like proper hexagonal honeycomb structure arrangement. So this hexagonal structure changes at these defects region. So the atom distribution changes, hence the electrons are changes. So electronic distributions are changing. Since the electronic distributions are changing, overall electrical properties are changing, or let's say localized electronic properties are changing. So that is we have found, oh my God, these wrinkles are altering the native property of the material. So that's the reason behind of the research. But there's a down part. We got the answer. Okay, because of the number of the wrinkles, number of the other defects, grain boundaries are halting the reproducibility of the results all over the world. But there's an upside also. Then we are saying, since they are changing the property, and not everywhere, locally, it's something like that. You have a body ache, but not you have an ache, but not in whole body. Somewhere, like only at the shoulder. So wrinkles are affecting locally, not everywhere. Then we were thinking, if they're affecting locally, we will use it some way? Then we have found, yes, if we make a wrinkles as we define wrinkles properly in arrangement, proper periodic arrangement, we can make something a kind of like a different doping regions. Doping is all using the transistors and the diodes. So we have found the wrinkle region is basic in case of the graphene on silicon system. So if there's a wrinkle there, the particular wrinkle region act as a less speed dope system. Graphene on silicon, when it is flat, it is p-doped system. And when there's a wrinkle, there's a less p-dope. Consider it N. So we got like world tiniest PNP junction. And means the dimension of the wrinkle is act as a basically a doping region. Although we have not introduced any foreign material, it is just a same material. Just it is not connecting with the substrate. It changed the property, and we got, wow, just change the gap, you can change the material. So that's why the concept of the tiniest, the PNP or transistors is come into play in this research. So now your second question was elaborate and the findings also. Yes, so it's not only you, all other reporters that we have discussed this year, they have asked that, can you reproduce, like wherever you want, you can produce the wrinkles, because it is not easy. The answer is now yes, we have found a very good strategy that we can produce the wrinkles in this 2D materials wherever we want. And the answer lies that nature already giving us a hint, like aging of a people, we get wrinkle. So we follow that path. So it's a kinds of the following the nature. We have found that when you get old, your outer surface of the skin is stiffer than the internal skin, like called epidermis and dermis. So these change in the mechanical property, the outer layer shrinks the inner layer, means when you get old. So that's why you get aged wrinkle. So we have found, okay, let's meet to other material. Let's put graphene on something which is softer rather than on silicon wafer. Then we have found, yes, exactly, things are happening. We are generating the wrinkles wherever we want. So another strategy that we have adopted is
yes. I want to jump in real quick, and so it sounded like that there were, some benefits to introducing these wrinkles, in terms of improving the electrical properties, and that.
No, the answer is no. These are disorders. So you cannot improve the electrical properties, but you change the electrical properties. Sometimes change is required rather than improvement. I can give you an example. Graphene itself, if it has no defect, it is useless for switchable devices. Okay, you cannot switch it. You need a semiconductor. That's why the copper is not using in the semiconductor industries, and we need a kind of band gap to use the switchable, like on off 1 0. You need one. It will remain on, like it will remain 1. It will always be 1 0. It will always 0. You need a 1 0 1 0 kind of arrangement. So switching is required. When you switch off it, it should be flip it down. It should give another signal. That is missing in the graphene. So these wrinkles are introducing these semiconducting behavior, because if I go fundamentally, the direct cone of the graphene are touching, like let's say the band gaps are touching each other. But if there are some defects, or depends on the density of the defects, this band gap changes. So the non-metallic nature of the graphene transforms to the semiconducting nature. So that's one beauty of the wrinkles. Of course, mechanical integrity will be compromised. You will not get steel base material, but in electronics, you do not need it. You do not need like armor in electronic industries. So here the electrical properties are sufficient. One more interesting information that I can tell you, which is hardly explored, but we have recently submitted a paper. These defects also increase the Joule heating effect. It means the thermal performance basically degrade, but it increased the temperature. So we have found that this work is in collaboration with the KAUST. Professor Omer is in charge there. So we have produced the CVD graphene nearly 100 nanometer thick, and it has lots of wrinkles and some edges. So when we give a potential bias around 7 volt, which is not so high, your mobile charge at nearly 5 volt. So we are getting a temperature up to 300 degrees centigrade, and we have continuously heated it at 12 days. Nothing happened to it. So just with a 7 volt, you can get 300 degrees centigrade. It means the continuous performance was nearly 250 degrees centigrade. It means it is a massive application in space and getting yourself heated in the space, or like going anywhere in the world or at the colder region at the very cheapest way. So you don't need a very high like potential bias to get the heater. So these are and you don't need any metal. That's the good thing. You just need carbon. Carbon means you don't need to add any copper, any rare earth material to get that heating. So these graphene heaters are also interesting. That is coming up, and it might be useful in the future as well. So thermal, electric, okay, mechanical, yes, as well. So
excellent. So the graphene heaters could maintain higher temperatures in transmitting electricity and maintaining the flow of electrons.
Yes, we can say something like that. Actually, graphene is a very good thermal conductor, but the presence, so it means it a good thermal conductor means it's act like a metal. You know, you touch it, you get heat energy, you can feel it. But it means that the temperature will not rise, because it will go away. So how to hold the temperature? You need to add some defects. Means defects is not a good term. Structural disorder in the material. So these structural disorder alter the path of the thermal influence electron, and that's why the path of the electron get drifted, and they hit each other, or with the defect center, the material get heated. It's a part of the Joule heating effect. So that's the graphene is means that's the structural disorder inducing the graphene. So if you increase the more structural disorder, the temperature will rise, but there should be a limit, because it is eventually a carbon material, and when you're heating in air condition, maybe you might not able to reach up to 500 degrees centigrade, because it will degrade the material itself. But with the optimized number of defects, we got a sustainable graphene heater with the tunable amount of the structural disorder, and of course very regulated potential bias.
So it's almost as if the electrons, they're like riding a wave along the curtain of
Yes,
the wrinkle.
kind of. So what curtains are doing? Basically, they are a speed breaker. So these speed breakers are slowing down, causing the heating, or collision between the electron is causing, because when there is like a, so there's a difference between a highway and when you have lots of speed breakers. So these things are acting like that at the nanoscale. That's why the material heats up efficiently. When I said efficiently, means with the less potential bias, and you can reach up to nearly 300 degrees centigrade. And this is, I don't think someone has recorded such high temperature. Means people has done something with graphene oxide and other stuff, but they hardly go beyond 100, or maybe some people has done with the carbon has to up to 200, but 300 is no one has reported yet. Just a pure carbon, no doping, nothing.
That's amazing.
Yes.
And so you guys essentially, it sounds like you made these like tiny microchips that are 100 times smaller than typical microchips.
Microchips fabrication is the last goal, because first we have to make transistors. Okay, so then the second thing is the assembly of the transistors, then the packing of the transistors, and then the chip come. So it's we are now at the second stage. We like in the January, like last year, we have decoded this. how this single wrinkle is affecting as a world tiniest transistor. But now we are encountering the problem that the periodic arrangement of the wrinkles that we can get wherever we want the wrinkle. So that is called, like, the assembly line of the transistors is needed. So we are working in that direction. But when the assembly line will done, then the compactness and then the chip manufacturing will come. But it needs some industrial collaboration, because we need some problem to understand what the things they are looking. For example, the height of the wrinkle, this is your second question, the height of the wrinkles also affecting the properties. So that I will come a bit later when you will ask. So chip designing is slightly far. When I say slightly, I could say that 5 to 10 years.
Gotcha. Very cool. It's exciting research and work you're up to. And so in your publication entitled "The Structural Defects of the Electronic and Nanomechanical Properties of 2D Materials," you looks like there were these things called deflated graphene nanobubbles that were important.
These are, as I said, when the material is flat, it considered as a pure and pristine. Any structural disorder, bubble, wrinkle, even we have addressed different shape of wrinkles. I think there's a question about, you have asked flex, standing collapse wrinkle or bending wrinkle. So we found that different shape, density, height of these structural defects alters the electrical and mechanical property differently. It means the upside is basically you are making a new kind of periodic table just by this. If you have lots of bubbles, you have a different material. You have a wrinkle, you have a different material. You have a different shape of the wrinkle, you have different material. A single carbon element like graphene is making its own periodic table in its way. So that is the beauty of this part of the research. You can, without addition, for example, in case of steel, you have iron and carbon. So you are adding something. But in this, you are not doing anything. You are just changing the shape of the material and you are getting a different material, a new material. That is also kind of like, the first carbon is abundant, not unlike like metal and other stuff. You are replacing other material which is required. You make graphene semiconductor, you make graphene highly conductive wherever. It's the same material using everywhere.
And as we were alluding to the electronics manufacturing, what exactly is Straintronics, and why are they kind of disrupting the electronics manufacturing?
Yeah, sure. It is an emerging field, and strain. It definitely, you can understood that it is a confusion of two words, strain and electronics. So it means that you induce the strain in the material. It means you stretch, compress a material, and you get a new material. But it has some limitation also. Those materials which are brittle in character are not part of this category. For example, silicon, indium tin oxide, which you use in your mobile screen, they are not flexible. So you cannot do flexible electronics with this material. These materials are focused in a very limited application, like flexible electronics. For example, the clothes that you are wearing, if you have a graphene in it, it can sense your heat, or even it can give you heat. Okay, so you can have a graphene device or somewhere the patches, and you can go out maybe in the colder region, it can provide you sensing, heating, and other interesting stuff. But and with the stretching, and since it is flexible, so it is changing its property. But those material like glass, brittle, having a property, they are not come in the category. So this is the first drawback. Second problem that the industry is facing is that it is difficult to control the strain. Strain is about change in length upon original length. It means that when you stretch the material, the length changes. So it is difficult to control this. When, for example, let's say at 0.2% of strain, you are getting a different material, then you have to maintain this strain throughout the material. Otherwise, if you get some region, you get the 0.3 or 0.5 strain, the material will be more semiconductive because the band gap changes. So that is a difficult part. In laboratory, we have some tiny chips, like, you know, in the laboratory scale, we are just working on the 1 centimeter square chips. But in industry, it will be massive. So holding the strain distribution or the stress distribution along the 2D material, it is not that easy. So that is the problem that basically two problem. The brittle material are not coming in the category. Second, the strain distribution is not easy. We found one solution for that strain distribution, but it's pretty expensive. So that's another thing. Industry will think 100 times before doing that. It is the recent work that we have published in small. So we have done a texturing, but we changes the periodicity. For example, in one case, the textured, the grooves are very close to each other, let's say 40 nanometer. And then we, sorry, gradually increase the spacing of the groove. And then we deposit graphene on it, single layer graphene on it. So graphene, wherever smaller groove separations are there, low periodicity, they have one kind of strain. And then they have another periodicity, which is higher. It has another kind of strain. So and this strain is forever because the textured samples are irrevocable. So we generated the same silicon, same graphene of different strains. So that's a very good example. But you need a laser technique for the ablation, for the, I mean, at the laboratory still it is possible, but it will be very expensive at the industrial scale. Means we have to think something in that direction. Otherwise, when you stretch a material, it is dynamically, it is difficult to hold this situation for long time. So that is the thing we are not getting. Another thing that we have to be careful, the straining and all this thing need not necessarily can improve the property of the material. No, as I said, when you have a proper pristine material flat, when you stretch it, it changes. I think, oh shit, the change is required, not the improvement is required here. Graphene itself is a very superlative material and very high conductivity and all. So slightly change can give more application rather than improving it. Even if we can, if we really want to improve it, just remove the defects. You will improve the material at all. But sometimes the changes are required for the selectivity and all. So here now the question here comes the role of the grain boundaries that I'll come a bit later.
Yes, we were wondering about those the grain boundaries and the different kinds of wrinkles and
yes. Talking about the nature of the wrinkles, let's start from something. So when the graphene is flat, no defect, okay, no structural disorder. So when there is a gap, the hump of less than or around 1 nanometer, it considered in the category of ripples. So when you do the nanoscale imaging, it's look like a wavy structure, like wave that we can see in the oceans, small, tiny hump. When this hump go from 1 nanometer to 8 nanometer, and it changes the property because the gap is increasing. So it becomes a standing collapse wrinkle. If you want to imagine a standing collapse wrinkle, one of the very good example is the gents toilet. There's an image of men and women begins there. So there is a head, there is a like a body, and then there is a feet. So standing collapse wrinkle exactly look like that. So the legs are joined together, and the head is a top head also of the wrinkles, and the feet are just slightly far apart. So the collapse part is the legs when they are contact to each other. So that's, I'm giving you the manifestation how the standing collapse wrinkle look like, and it's lie up to the 8 nanometer to 12. It varies. However, when you reach the maximum limit of 16 nanometer of the wrinkle height, it start bending. Whatever I'm talking about, just an atomic layer of graphene. If you have a thicker layer of graphene, you can go even up to beyond height. But just I'm talking about the atomic layer. So if you have an atomic layer, and then you can maximum achieve around 16 nanometer, then it start bending, because the bending stiffness is not enormous in the single layer of graphene. You can manifest like an old person having a stick, but just minus the stick. So it's like start bending, because when it's exactly like, those trees which get too tall, it start bending. So that is, and when this bending is too much, it's close to the surface, like it bend too much, bend down, like someone in Islamic, they pray the way they pray. So it's like a fold. Now they are in a folding state of the wrinkle. So and each state of the wrinkle giving you a different property. So we have addressed this in our paper, like different stages of the shape and the bending of the paper, building of the wrinkle. So these are the ripple, standing collapse, and the folded state. Now the grain boundaries. Grain boundaries you can manifest as there is a cloth, someone had tear it, and then you stitch it. Okay, but how it generates, because all these graphene usually come from metal, because there's a process called chemical vapor deposition or pulse vapor deposition. So they grow graphene on polycrystalline metal, and these metal have different domains. Each domain has different arrangement of atoms. So graphene mimics the metal. So when you take it off from the metal, so the interfaces between these domains are domains called grain boundaries. So that's where the word has come from. The beauty of the grain boundary is it is very selective to the gas sensing. The bad point of the grain boundary is it make things weaker, because stitched material is always poorer than the original material. So even your cloth get torn apart, if you stitch it, it doesn't have the same mechanical integrity as the original material has. But in the nanoscale, there's one paper, not by our group, someone has found that the gas sensing ability of the grain boundaries are nearly 300 times higher than a pristine graphene material. So how it happened? Because change in the electrical and mechanical property. So that is the beauty of having the grain boundary. Means you cannot use it as I said, for the mechanical property, but you can use it as a sensor.
Sounds impressive, yes. And so I'm trying to wrap my head around this gas sensing, and it sounds like the graphene can better kind of detect the gaseous molecules around it, or
Yes and no.
okay.
Yes means the sensitivity of the graphene is so high that it's never ever seen by mankind yet. There's one paper from Manchester group. They have found they can detect they can sense one molecule. However, the sensitivity is high doesn't mean selectivity is high. Means, let's say it can detect one kind of gas. Let's say imagine nitrogen dioxide. It can detect, but it can detect the same sulfur dioxide. So the sensitivity is missing, because the graphene is pristine. It behaves everywhere the same way. So here you need a selectivity. So that's why the role of the selectivity comes. There are two things. Either you dope the graphene, like let's say you add some extra material that will sit on graphene, and they will change the chemical or electrical property locally, and then they are more affinity. They have more high affinity toward the foreign molecules, which is going to detect. Other thing is that you introduce the defects, through laser, make holes, or you make structural disorders. They have a different chemical and electrical property, and they can sense it differently. So, so graphene, so it means that if you want to use the graphene for space exploration, like getting a tiny details, then pure graphene is good. But if you want to use in your daily life, like COVID sensing, making COVID sensor, ammonia sensor, carbon dioxide sensor, nitrogen dioxide sensor, or even war gases like DMMP, other stuff, then you have to add some kind of selectivity in the material through doping or through by structural disorder. So you need, it means your graphene then can sense different amount of gases rather than just on the one gases. So that's the answer of yes and no. So it is great. It can get the tiniest, but the selectivity is missing. So you decrease the conductivity by introducing the defects, but it can detect a different amount of gases. So that's the the catch we have to understand.
It's so cool. And so these so I was reading about how the previous studies, created similar kinks or wrinkles to develop highly sensitive cancer biosensors too, and water filters, and for next generation batteries, and it looks like they could make they hold the potential, these 2D sheets of graphene, to make lithium ion batteries 18 times more potent, and improve solar panels and all sorts of exciting things. I was wondering if you could elaborate more on some of this research and how these capabilities are enabled. Yes.
Sure. But these actually graphene or other 2D materials, they are showing different properties in different field, and each application that you are pointing, either the battery or the water filtration, they are just targeting a particular property. Let's start with the easy one, the filtration. The graphene is if you consider as a membrane, it is like as a mesh which won't allow anything to go here and there. Or if you make a tiny hole through laser, through a particular size, then it can allow only that part of the material. Let's say you make a hole of some hydronium ion or some proper calcium ion, then only that can go. But usually the space between these two material, I think, are nearly in picometer range, 160 to 170 picometers. You won't allow anything. Only hydrogen positive ion can go. So this thing is very fantastic to do the water filtration. So it can allow few kind of ions that, or just water molecules, or the heavier ions or the contaminants, it can block easily. So that's a part of that's like a physical membrane application. You are using the physical property or the membrane property of the graphene. In the battery application, it is different. Here you are using the conductive performance of the graphene, the flow of the charge of being conductor. In the first part, the conductivity has no rule, neither the mechanical, but just we are using as a membrane. The second part, how it supports the flow of the charge, it making the bridge of the charge to the one material to the another material. Usually, many researchers are proposing of replacing the graphite, because when the lithium ion, especially in the case of the lithium ion batteries, when the lithium goes to the traditional graphite, then it swells. Okay, and the area increases. Maybe you have seen some regions of the battery get swell. So it's because of that, because of them, the lithium ions can absorb the graphite, the surface area increases and it gets swell. So in the case of the graphene, it can adjust more, or it can provide a better, but not they're using as a graphene, using a graphene aerogel, which is a very porous structure. So then it can adjust, or it can accommodate more lithium ion, and that's why the performance of the overall battery will be very high. One interesting information I can tell you is people are also using to protecting the corrosion, but it is not graphene. It is its sibling called HBN, hexagonal boron nitride. It's a similar material like graphene, but in spite of carbon, it is alternate like positions of, sorry, boron and nitrogen. So it can protect for the corrosion, and corrosion is a massive problem because all the metals that we are using in marine, even going to use in for space application, they need to be protected against many harsh environments. So that's a thing is needed, like also like in future. What else you have asked? So battery, membrane,
Yeah, I
and
was
something
also
else?
reading about how the graphene sheets could make carbon fiber 225% stronger and 184% stiffer. Um,
Um, it is it's a catch actually. How much amount of the graphene you add in the fiber, that plays a very important role. It is exactly like when you are polymer, it is softer, and then you add a graphene like material, and they have to be integrated well. This is the catch. It has to be integrated well with the matrix, then the material become stiffer. So that's a thing. Otherwise, if you do not do the math properly, the carbon material itself act as a defect center, because you are introducing a foreign material in the polymer, and the quality compromises. So the good news is that you don't need to add too much. You just need to add something fraction of weight percentage, 0.1, maximum to 1 weight percentage, and you increases the mechanical property very stronger. It depends on the interaction between the polymer matrix and the carbon. Usually you have to use the functionalized graphene rather than functionalized means you need to add some oxygen group with the graphene called graphene oxide, so it can integrate well with the polymer and increase the property of overall polymer matrix. So that's a catch that you have to think a bit about it. So usually functionalized graphene are better than the pure graphene for increasing the mechanical properties of the polymer composites or any kind of fiber.
nice. And we can use carbon fiber for all sorts of materials and structures, you know, and spacecraft and payloads and propellant, cryogenic tanks, and energy storage.
Yes, actually, when I found this question, it was very interesting, but graphene can do more thing actually. Not only this the carbon fiber stuff. First thing is that it is a lightweight, and those who are involved in the space exploration, the weight is a very main concern, because it's cost you a very large amount of fuel. So the carbon fibers are stiffer, and they are also thermally resistant. It cannot allow the heat outside to get in. So these are the very interesting requirement that is that carbon fibers are providing. However, I think some research has to be done also, because there is also a radiation in a space. So, and maybe these carbon fiber has to be some kind of coating that can protect the aircraft overall. I'm not talking about lead coating. Means something new, maybe it's from this 2D material that can protect the surface of the aircraft against the radiation. Or moreover, maybe one can harness the radiation, because radiation is kind of very high energy, can into some useful form of energy, maybe some kind of piezoelectricity or something like that, you can get the energy even from the radiation in the space. So yes, this is the research that I think it's going to be in future soon, because I know the space race has begun all over the world, and lots of things are getting commercialization. So the safety and the economy both are dire requirement in this case. So I think those 2D materials who are useful against radiation, or who can perform well or harness the radiation energy, that will be a game changer.
Yeah, that harnessing the radiation seems promising as well.
But I don't think carbon, the carbon is a very light material. It itself cannot do anything. So I think it needs a combination of other 2D materials who can either absorb or harness or convert radiation energy into something else. Maybe some kind of doping with boron or boron, something like that. Means this is not my extreme expertise here. But for example, carbon boron nodes are using as a moderator, but I don't know how much its capacity to absorb the radiation in the nuclear reactor. So, but I think in the family of 5,000 2D material, there or some combination will be there where we can get a very good hybrid layers where we can protect or harness both the radiation energy. But that will be because if you're thinking, because in your question you are thinking about the Mars, so the space is brutal and Mars is not merciful like our Mother Earth. So both are very, very difficult situation, and radiation storms will be there definitely. So you need extraordinary materials. Graphene is definitely one of them in terms of providing conductivity, in terms of providing heating and lightweight. But we still have to look for those materials who can protect against the radiations. And some and not only that, we also need a material who can protect us against some alien microbes. I'm not talking about alien people, but alien microbes, which means the human nature is not encountered yet. So we need those kind of sensors to detect them, and because once you detect it, then you can protect it. So these extraordinary materials are needed. Yes.
Yes, wonder if we could help absorb some of the incoming galactic cosmic rays with those, graphene nanomaterials and structures.
Yes, I think it is possible because the sensitivity of the graphene is extremely high. No other metal has reported yet.
I'll
Yes.
have to take a deeper dive. Yes.
Pardon?
We'll have to take a deeper dive into this one. It's exciting.
Yeah. Yes. But it comes with the cost. These super sensitive materials are not easy to make. But there's a paper in 2008 by Manchester Group in Nature. I forgot its title, but they have shown that graphene can detect, in fact, up to one molecule. And that was really fascinating paper.
Nice. And I think like one or two more things here. So coming back to the graphene sheets and Straintronics, where toward the later end of the electronics manufacturing, to the Straintronics was that we could make more space inside the microchips for more electronic materials, and it's kind of like this nano-origami
Yes,
game.
yes. Answer is yes, we can make it. I can give you a very good analogy. See, I'm from India, so we cannot have like a facility that's how we have housing culture here in UK. we have here people have some their own houses, but in India you have multi-stories. It means when the land is occupied, the sky is the solution. This is exactly what we are doing in a chip. So when the no surface is available, you have to look up, and graphenes are the thing that you are looking up. So what it is happening, you are mounting, technically you are mounting carbon layer over carbon layer, giving them height. Let's say carbon rods you are making. I will not call them rod because they are not touching to the surface. They are like levitating, kind of like that. Or they have an arrangement that is not touching the surface. So I'm not calling them rod. So in this way, you are having a higher number of the PN junctions as compared to the traditional. This P part, so it's PNP junction. So we have done this. These are the strategies that, so the thickness, oh sorry, not thickness, the width of this wrinkle are in the nanometer range, something like 1 to 2 nanometer. So in this case, means particularly in this case, so you can adapt more and more kind of transistors per unit area. I think the present processor, the top quality that made by the industries is up to 25, and this is smaller than that. This is like 1/5 of more. So you are increasing nearly 5 to 6 times more number of the transistors as presently exist. As I was saying,
Yes.
yes.
Yeah, and it sounds like that that increase in transistors and just the making these really small computer chips could, I was reading, it could make our computers and phones 1,000 times faster.
Yes, indeed. Yes, more number of these chips. There's some problem. More number of the chips can give you the more faster performance. So yes, so it is true. So if one can ask that how you are designing this, so we are actually present at these two stages. That, as I said, we are regulating the density of the wrinkles. So for example, here we are making textured surfaces through laser, and we deposit graphene. Actually, the key is the gap has to be there. So this part should not touch the surface. So here we have found when the graphene is suspending and not touching, so we have find a different electronic property as a part which is touching the surface. This is a schematic, something like that. So here we can get P and P. And this is one of we are planning to submit in a Nature Physics next year. So here it is a hybrid system. You can clearly see that on the left hand side, we have a flat surface, but on the right hand side, we have a high density of the wrinkles. Basically, graphene is everywhere, but it is only appears on the MOS2 because, as I said, we decode this part of the mechanics and the interfacial science between graphene and another 2D material that can create the wrinkle wherever you like it. So now we are in this. So the third step will be, as I said, making the assembly line, and then the compactness, and then the chip manufacturing. So it's a long way to go, but we are moving like in a good pace, I could say that. The third strategy, which I will give credit to our collaborator in Rice University, Professor Ajahn. So he said that if you have a liquid phase material in beneath, you can, and that is also electronic or semiconducting, you can digitally or through artificial intelligence, you can control the density of the wrinkle. One of the very clear examples you can see in our daily life, this is my morning tea mug. You can see a wrinkle of the top cream over my my tea, which is liquid. So the liquid phase is very much helpful in creating the wrinkles of the top layer. So there's a very, so if we have a liquid phase material beneath, or a material which can convert into liquid, or we can digitally control the liquidity, means many of the semiconductor like gallium are like that. So this is the future of the plan that we are thinking. We can, using the phase change material, we can generate further density of the wrinkles electrically wherever we want. So it's now it sounds like fiction, but it is possible.
Congratulations, Manoj. It's very exciting research you're doing, and I can't wait to read more. And thank you for sharing this.
So, which question I miss?
I think that's most of our questions here. But yeah,
there's one question you are talking about. What are the research areas would you advise research and investigate?
Yeah, kind of along the lines of the enabling the ultra low frictional forces with the nanomechanical systems.
Oh, okay, that's actually a very interesting one, but it might take a couple of minutes. But I will ask you a question. I think you are in US. You definitely have a car and you put the engine oil. Okay, because there is a gear system that are rotating and it needs to be lubricated. Just imagine if your gear system is of 5-10 nanometer. You can't add oil. You can't. Your nanorobots are basically 5 to 10 or maximum 50, 100, means they are in the nanometer range, like 1 to 100 nanometer. If your nanorobots are working, like rotating, they're because of rotation, there is a friction generated. That friction is causing heat. That heat is, if it accumulated, it can destroy your nanorobot. What you can do, you cannot do anything, because the size of the machine is more than a droplet. It's very smaller than a droplet, and so you cannot use it. If you put one drop, it is a micro size. So you need atomic layer to protect your nanorobots. So that's a part of the project. So these nanorobots could be for the civilian application, defense application, anything. It doesn't matter the application. The concept is how to protect those nanorobots. So we have done some coating of graphene, single layer graphene on this serrated, like gear shaped structure. And we have found and then we rub against another gear structure, which is through the technique called friction force microscopy. So in which just you have a coated material and then you rub against each other. So we found that the coated region of the graphene is showing a friction values nearly 1/10 of the bare silicon. We have used a silicon system as a surface, because most of the robots are here making using silicon devices. So this was a benchmark to understand. So that's why you are protecting the graphene through the graphene covered system. The fundamental value that we have found, the graphene is not accumulating the frictional energy, like friction induced heat energy. It dissipates easily. So it means that your gear system will not accumulate the heat. It can protect. When it distributes, the whole system get durable. So I do not. This is a very new technology. We do not know how much the sustainable life the nanorobot will have. But if I go with the present value, it can increase up to 10 times. Like if you're in a present case, if it is surviving, like say 5 days, then with graphene coating, definitely maybe more than 50 days, something like that. So these things, this is the thing that we have uh, found for how in the case of the nanorobots, which is another possible the future investigation people are working how to protect those devices. But not only that, graphene being conductive, if something gone wrong with the device, it can give you a signal that something gone wrong, because it is easy to get a signal from a drone and from plane, but it is very difficult to get signal from a nanorobot. So graphene can also, because here the change in the conductivity will play a role, because we get one kind of conductivity when the device, when the nanorobot was working. If something gone wrong, it changed the conductivity and we get the signal that something gone wrong with the device. So this is another like a fascinating research in terms of the nanoscale robotics and friction.
That's awesome. Yes. Look forward to, taking a deeper dive into these nanorobots and graphene coatings.
Yes. No, it is really interesting, and that's part of the research give us a very good idea of the Straintronics, because when we were working on this kind of work, this kind of textured surfaces, so we found that graphene is stretching differently on different textured surfaces, and each basically it's a whole single silicon wafer, so everything over there just different in the spacing. We have found different strain in the graphene, and each strain is acting differently. So that's why we are thinking, oh, wow, it's a typical field of Straintronics. So the graphene is same, but just the spacing between the texture changing its property and changing stuff. Right now, we just look at the friction aspect. The next part, we are going to the sensor aspect, because for example, so graphene on a nanoscopic texture, how it's sensing again different gases versus graphene on bigger texture, like when the spacing is different. It's a kind of, we are trying to provide a selectivity just by strain in the material. So again, I'm saying I'm not adding any arsenic, phosphorus, or nitrogen for doping. I'm just straining the material differently and getting the different selectivity.
Wonderful. Well, we've learned so much, and I'm sure everyone else has listening. So we're pushing the hour, but keep up the great, inspiring research and work over there, the University of Sussex. Yes.
Okay, cool. Thanks for your time, and let me know if something is not clear, and I will try to explain. I can write a draft for you for that to make it more clear.
Yes. Enjoy your holidays.
Okay, thank you. Same to you. Bye.
Bye.